Welcome to Summarize Science. Today, we're diving into a paper that could change how we train the biggest AI models. Most large AI, like the ones that power chatbots, are trained using a method called backpropagation, which requires calculating gradients. But what if a task is noisy or the AI structure is non-differentiable? That's where evolution strategies, or ES, come in. ES works like natural selection. It creates a population of slightly different AI models, sees which ones perform best, and combines their traits to create the next generation. The problem is, for models with billions of parameters, creating and testing this massive population is incredibly slow and expensive. This is the bottleneck that researchers tackled with a new method they call EGGROLL, evolution-guided general optimization via low-rank learning. Here's the genius idea, visualized in this diagram. Instead of creating massive, full-rank perturbations for each model, EGGROLL uses small, efficient, low-rank perturbations. Think of it like this. Instead of changing every single pixel in an image slightly, you just change one simple line or gradient. By combining many of these simple, cheap changes from many different models in the population, the final update to the main model is still complex and high quality. And the results are staggering. This graph shows the relative speed of EGGROLL compared to prior methods. The researchers report up to 100-fold increase in training throughput for billion-parameter models, nearly reaching the speed of just running the model without any training at all. This efficiency gain is what allows them to apply ES at a hyperscale never seen before. So, what can you do with this newfound power? The researchers demonstrated 3 fascinating applications. First, they built and trained a language model that operates purely on integers. Because EGGROLL doesn't need gradients, it can handle the nonlinearities of integer math, which is a huge step for creating more energy-efficient AI hardware. This graph shows their integer-only model training stably across massive population sizes up to over 260,000, something very difficult to achieve with standard methods. Second, in the world of reinforcement learning, where AIs learn to master tasks like games, EGGROLL proved to be highly competitive with, and in many cases, better than standard ES methods. These charts show its performance across a variety of complex environments, proving it doesn't compromise on quality despite being much faster. And third, they applied EGGROLL to fine-tune large language models for reasoning tasks. On math reasoning benchmarks, their method outperformed a popular technique called GRPO, achieving higher accuracy in the same amount of time. This demonstrates its potential for making our existing large models even smarter. So let's recap the key points. The EGGROLL method makes evolution strategies practical for today's massive, billion-parameter AI models by using efficient low-rank perturbations. This results in huge speedups, enabling applications like training integer-only networks and outperforming existing methods in reinforcement learning and LLM fine-tuning. What does this mean for the future? This work could unlock new types of AI architectures that are currently impossible to train with gradient-based methods. Imagine training neural networks that directly interface with symbolic modules for memory or calculations, creating more robust and understandable end-to-end systems. EGGROLL is a powerful new tool in the AI toolkit, pushing the boundaries of what's possible at the absolute hyperscale of modern machine learning.